Chapter 4 is about complex numbers, and you've likely seen complex numbers before, but we're going to discuss them here because they also have a trigonometric form. So first, in section 4.1, we're just going to talk about complex numbers the way that we already know them, so just kind of a review probably for most of you, and then we'll talk about the trigonometric form. All right, so complex numbers involve the imaginary unit I. There are some quadratic equations that don't have any real numbers as solutions, so mathematicians expanded our number system to include imaginary numbers. So the definition of this imaginary I is that it is equal to the square root of -1. The square root of -1 would be the number that we square to get -1. But if we square any real number, whether it be positive or negative, the result is always a positive number. So anytime you take the square root of a negative number, then your answer needs to involve an I. The answer is imaginary. So if we add real numbers or multiples of real numbers to this imaginary unit I, then we end up with a complex number. So every complex number can be written in standard form. And standard form is A plus BI. So A is the real part and the BI is the imaginary part of a complex number. So an example, just a quick example here, if we had something like this, and we wanted to put it in standard form, then we need to evaluate that square root. And we do know the square root of 4 is 2, but since it is negative, we need to make sure we put I on our solution here. So 2I is the square root of -4. And now you can see this is written in this A plus BI form, so we would say it's in standard form. So this is a complex number in standard form. So let me just label them here, that A is the real part and BI is the imaginary part. So here this B is a real number and it is multiplied by the I. That is the imaginary part of a complex number. If a complex number has no real part, so something in the form just BI, we would call that a purely imaginary number, as long as B is not equal to 0. Okay, so now let's do a few operations with complex numbers. Addition and subtraction with complex numbers is essentially just like combining like terms. So you can add real parts to real parts and you add the imaginary parts to the imaginary parts. So something like all of this is addition. So if I just want to add these, I'm just collecting the like terms. So the 3 and the 6, those are real numbers. I can add those two together. And then the I and the 4i, those are both imaginary. I can add them together. Important to remember here that the coefficient on the I is just 1. So just like if they were x's, so we got 1i plus 4i's. Okay, so adding those together, 3 plus 6 is 9. 1i plus 4i gives me 5i's. So writing that answer in standard form, I would write 9 plus 5i. So adding the real parts to the real parts, imaginary parts to the imaginary parts. Subtraction is the same, except with subtraction, you do have to be careful about the order and parentheses. Those do make a difference. So you can do it just like you would if I was any other variable. And so I would just distribute this negative to clear the parentheses. So essentially multiply -1 times 16 and then -1 times -8. And that's going to change the signs, but it gets rid of the parentheses. So now I can just add. So it's the same as doing like your leave change opposite when you're adding integers, change it all to addition. And now I'm combining like terms. So I'm going to combine these imaginary parts. So 14 plus 8 is 22. So I've got 22 out minus 16. And this is acceptable for standard form. If you move them around, so if you wanted to put the real part first, which again, you don't have to do, but if you do, just make sure that you take the negative with the 16. So if you move them around, the 16 is still negative, the 22 is still positive. Multiplication with complex numbers, again, very similar. Complex numbers, they have all the same operations that we've got with our real numbers. They're associative, commutative. The distributive property over multiplication works with complex numbers as well. So if you had something where you are multiplying two complex numbers, you could FOIL this if you like FOIL. I would prefer to just distribute. So I would just be distributing 6 and then distributing the 5i. There is one thing that's different here when you multiply an I times an I. Since I is equal to the square root of -1, if I multiply it by itself or square it, if I square the square root of -1, I just get -1. So when you're multiplying, you end up with an I squared. You don't want to leave it I squared. You want to change it to -1 so that you can simplify. So I'm going to multiply 6 times 3, and then 6 times -2i. So that'll give me a -12i. And now I'm going to multiply -5i times 3, -15i. And then the -5i and the -2i gives me a positive 10i squared. So I'm multiplying I times I. So now I'm going to change that I squared to -1. And this is multiplication, so it's going to be 10 times -1. So the I squared is equal to -1, so just replacing them. And now, to finish this up, I just need to combine the like terms. Well, let me go ahead and multiply this. 10 times -1. That'll make that -10. And now I can combine the real numbers, and I can combine the imaginary numbers in the middle. And so I end up with 8 for my real part and -27i for my imaginary part. So you're just FOILing it and combining like terms. The extra step is that the I squared becomes -1. All right, last thing in this section is complex conjugates. So for our standard complex number, a plus bi, its complex conjugate would just be a minus bi. So the same a and b, we're just changing the plus in the middle to a minus. That's all. A lot of times you will use a complex conjugate if you need it to simplify. So we'll do a division problem. We don't want to leave our i's in the denominator, so we will use a complex conjugate to simplify, to rewrite it in standard form. In the slides for this section, it does show what happens when you multiply a complex number by its conjugate all the way out, and you could do it here just with this a and b, but the I is going to simplify away. We'll get the I squared situation, it'll turn into -1, and we won't have any more i's. So that's the benefit of using a complex conjugate. So here's an example of a time we might use the complex conjugate. Something like this that's written as a quotient, and it's not in standard form written this way. I got that I in the denominator. So in order to rewrite this, I'm going to multiply on the top and the bottom by the complex conjugate of 1 minus I. So that would just be 1 plus I. So I'm going to multiply that on the top and the bottom. 1 plus I on the top and the bottom. So up top, that gives me 21 plus 21i. And in the bottom, FOILing that together, I'm supposed to do it all the way out. But we're going to end up with 1 times 1, 1 times positive I, 1 times negative I, and then negative I times positive I. So you should end up with this. And the middle terms should cancel each other and 2. One's positive, one's negative. That I squared, we know is going to be -1. Right, so now I've got 1 minus -1. Okay, so I've got this minus that was already there. The I squared is the -1. Put it in parentheses so it's not confusing me. And I'm going to enter with 21 minus 21i. And then that 1 minus -1 is just 2. So I'm fine with you leaving it like this. I think even web sign is fine with that. But if you literally want it to look like a plus bi, you would just separate this into 2 fractions. So 21/2 minus, wait a minute. I turned that plus into a minus just for no reason. This is still a plus. Okay, there we go. Plus 21/2. Okay, so this would be our standard. All right, so hopefully that looks familiar. The homework will give you some practice to refresh your memory on these things, and then we'll talk about the trigonometric form of complex number next.